This clip is about rolling motion. Rolling motion is a common problem in dynamics because in mechanics we encounter lots of kind of rotating gears and pulleys, and also if you look at like vehicles and it has wheels, so there's many things that roll on the surface area. Then we want to apply our knowledge about relative motion analysis to this rolling motion. And as you see that right now the cylinder roll on the surface without slipping. The reason that we don't include the case of slipping is because once the slipping is occur between the cylinder and ground, we have to consider the dynamic friction coefficient, and then we have to add another kind of constraint equations. So it becomes a little bit more complicated. So in here we just assume that there's no any slipping motion between cylinder and the ground. And if this is ideal circle cylinder, then you know that as this one is cylinder rotates, kind of roll, and this center G is going to move to the right. Right now the angular velocity and angular acceleration is clockwise. That's why it just moved to the right. Okay. Because this is circle, you know that the center just moved to the right with a certain velocity Vg. So this is center of mass, so that's why we call this a Vg. And then the ground doesn't move, right? So that means every point on the surface has zero velocity. And then at a given time, because the wheel it has a contact, so at any instance, the wheel has shared a contact point with the ground. By sharing the contact points whose velocity is zero, that means at a given instance the contact point has a zero velocity, which means the VA must be at zero. Then you know that we can analyze this motion as if this wheel is rotating about A at this instance at least. But in the physically everything is rotating about Y. However, when we analyze velocity or acceleration of any point on this cylinder, because we know that A is instantaneous zero velocity point, that's why we can analyze this motion as if everything is rotating about A at this instance at least. Okay. However, the A point has zero velocity, but it's not a point of zero acceleration. There might be accelerations of A at this instance. So let's talk about the velocity. Okay. Right now, if you want to express the velocity with certain omega, then our velocity Vg is equal to I want to use like relative velocity motion analysis. Then if you consider that the wheel is just translate like that, then the G point and A point has the same velocity, right? So as long as this is just translate without rotation, the Vg has the same as velocity Va. After it translated, then everything is rotating. Everything is rotates, right? Everything is rotate about A, then you can just write down using relative motion analysis the VA, and then we consider that everything is rotating about A. So the velocity of the G point should be omega, and cross product the position vector R G from A. Okay. Then we know that in the center, just move to the right, the center point can up and down. So if we use vector expression, the VG has only I components. And then right now, the contact point A has a zero velocity. And then the omega is clockwise. So put the negative K and cross product. This is R vector, so R is pointing up, so this is a radius R, and pointing up is J. So if you just do that, K cross product J is a negative I, so this is omega R I. So we know that your VG can be determined by omega times R. Okay. Or if I just use the vector form, which is VR and I components to the right. How about the acceleration? So right now, if you think about the acceleration of the center, it moves, because the G move along a straight line, the acceleration of center should be horizontal as well, which means your acceleration of center should be a certain component and I component, and 0 J components. So we know that it has only I components. We'll kind of roll, and then the A, this is just before A touch the ground. Okay, just before A touch ground, its velocity is directed downward, so the velocity is going down like that. Okay, just before A touch the ground, the velocity of A is directed downward, and this is points, contact points. And then just after contact, its velocity is directed upward. Okay. Thus, point A accelerates upward, okay, as it leaves the ground. So as it leaves the ground, the point A accelerates upward. So if I just show you another kind of animations to give you some ideas how the velocity and accelerations happening on this edge point. Right now the disk is just rolling, okay? And then if I describe the velocity of the point, so right now if you just look at the velocity of the A point, just before touch the ground it's just going down, but after touch the ground it's just going up, right? So if I just hide the disk, you see that this is change of the velocity. So the XY component velocity is going up and then going up and down. So that's why when the contact point is, the bottom point has a touching on the ground, it must be acceleration of A points, even though the velocity is 0. When it has a contact, when this one touch the ground. Okay. Let's just look at the accelerations here. So at this point, the A has the 0 velocity. However, it has certain acceleration y. Then let's try to determine what the acceleration would be. So in here, we also use relative motion analysis. AG is equal to AA. Right now, A is my base point, okay? And then once you do that, we also analyze as if this one is rotating about A. So that's why you can just write down like alpha and R GA, and omega square or r g a, like that. And then in g point here, the acceleration has only horizontal component, because the g point cannot move up and down, so I have only I component. And a, so as I told you that when this a is coming close to the ground and leave the ground, actually there's only the accelerations along the y component. There's no acceleration along the x. So we say a component has only y component accelerations, and then the alpha is clockwise, so this is negative alpha k, and r vector j, and omega square, and rj vector, like that. Then if you just do that j and jk, cross product is I, and this is omega square rj. So right now this is alpha ri plus aa minus omega square rj. So on the left side, you know that ag should be alpha r, and then aa should be omega square r. So the acceleration of g is determined by alpha r, and the acceleration of aa, so y component of accelerations, can be determined by omega square r. So this is the acceleration component of the rolling motion.